So great to meet everyone. I'm Orian. Today we're going to be talking about 3 different topics that we do at Decart. I'll try to give a quick overview on all 3 of them. And if you want to hear more details, you're welcome to talk to me afterwards. The first is our model called Lucy. We'll see it in a second. It's a live video editing model. The second is a model called Oasis. It's our world model that lets you generate the entire world from scratch. And the third is we're going to touch in a bit into the Decart optimization stack, which is what enables us to do real-time video generation for both of these first 2 applications and supports a wide variety of different hardware platforms. Okay, let's start with the demo. Live demos are always fun. So let me go here. And let's start Lucy 2. Okay, so what is a real-time video editing model? Well, on the one hand, it's like a regular image editing or video editing model in that it gets an input image or input video, it gets any textual prompt, and it just converts that into something else. The difference is here we're doing it frame by frame in real time. So here, for example, it was convert me into Mario. We can do convert me into a robot. Here we go. Convert into, okay. Convert into a zombie, convert into the Statue of Liberty. We can do that. See? And overall, the idea is any textual prompt you want. At the end of the day, it's a video diffusion model, which means it just learned all of these different topics based on seeing lots and lots of examples of images, of videos, of classified text. And then it knows how to generalize it to this editing case and to do any edit we want. So there you go. Now Statue of Liberty. And again, here are just a bunch of different examples. It wasn't even trained on these examples. It was just trained on everything, and you can do any text prompt you want to turn into that. Okay, so that was Lucy. Lucy started what we saw as the idea of what could happen if we took an image editing or video editing model and turned it into real time. But once you do that, you're opening up a wide new variety of applications that need that real-time aspect. That can function if it's a batch API, which a batch API would be submit a video, wait a minute, get back that edited video. You wanted something that is live. So one example is gaming. You could use this to take, for example, unskinned games, I don't know, regular Minecraft, turn it into anything you want. Take GTA 4, make it look like GTA 6. And we've seen lots of use cases around gaming of this idea of converting the entire world into something else. Different approach is live streaming. It already exploded on Twitch, where people are turning themselves into random characters on Twitch. Funny story, there's actually the chat that are bidding on what should the streamer turn into, and has become super popular on Twitch. Other applications, so one is e-commerce. One of the things you can do with the model is you can tell it, for example, to replace your clothes. So here we have some example use cases of you take any picture of a clothing item, you drag it onto the person, and then in real time you can try it on. It works for clothes, it works for different types of furniture, it works for a wide variety of applications. And you can also take this towards the approaches of types of ads. And at the end of the day, these are all use cases that are coming from the ability to do this in real time. Instead of having to do it, again, as a batch API, wait a minute to get back a 10-second clip, what could you do if you're doing it frame by frame in real time? Okay, the second live demo that we'll do, and then we'll dive a bit into the details, is going to be Oasis 3. This is a model that we released just last week. One sec, here we go. Okay, and the difference between Lucy and Oasis, so Lucy was conditional on input video, right? We gave it an input video and then we said convert it into something else. Here we're telling it to generate the entire world from scratch. So for example, here it's generating 3 different cameras from a car. You can choose the scene. So here, let's choose this scene. Again, just from a text description or an image, you can choose. And then it lets you simulate the world. So now I'm gonna press on the characters. So for example, now I'm pressing go forward. You can see on the bottom right that I'm choosing forward and the car is driving forward. I can turn to the right. And essentially what it's allowing me to do is simulate the entire real world using different types of actions. So in this demo, the actions, for example, are just WASD, steering, throttle, and that kind of stuff. But the model knows how to accept any action. And it also lets you essentially simulate different objects as they're happening in the real world. So you can see that while I'm staying still, there are different cars driving. You'll see pedestrians. And at the end of the day, this is letting you create an entire simulator of the real world that's conditioned on user actions. Okay. So what we just saw, Oasis, is a type of world model. A world model is essentially a video model whose purpose is to predict the entire world, to simulate it, and be conditioned on some actions. So they can use it to simulate the entire world. The first world model release was called Oasis 1, was roughly a year and a half ago. Oasis was a model that simulated Minecraft. It actually exploded on YouTube, TikTok, and Twitter, got to over 1 billion views. But that was a model that was able to just simulate Minecraft, and same approach. You're playing the game, but the diffusion model is behind everything. Since then, there have been other models coming out. So NVIDIA's Cosmos, Google Genie, and last week, the newly released Decart Oasis 3. So what can you do with these types of simulators? One approach that's really taking off recently is robotics. One of the largest barriers in robotics today is the sim-to-real gap. Essentially what that means is they train robots in simulators, simulators developed by NVIDIA, for example, Omniverse, but then when they try to deploy them in the real world, it's not the exact same. So for example, here on the left, you see a simulator, but everything is too clean. And then when they try to take a robot that was trained in the simulator, run it in the real world with a real camera, suddenly it's not as clean and the robot can just do random stuff. So for example, here we have on the left, this is a robot training inside a simulator called Omniverse with a policy from NVIDIA. And what you see is, let's play it again. When you give the robot input, the video as is, it's able to do lots of different stuff pretty well. So for example, here it's picking up a box, walking around, placing it on a table. The second we try to change the style, for example, so here we're changing the style to be dark or to be something else, suddenly the robot starts doing random stuff, starts falling, and won't be able to place the box. And the approach there is, for example, you could use Lucy to augment the training. Lucy's gonna let it see much more realistic environments instead of seeing only the simulator environment. And another approach would be combining this with Oasis so that you can just train everything inside the simulator. Once the models get big enough and get accurate enough, they're gonna get to the point where they not only look visually appealing, but they also have good modeling of physics and good memory, etc. And then you'll just be able to train the entire robot VLA inside the simulator. Okay, so that was a bit about the use cases. I'll give a quick background on how it works behind the scenes, and then we'll move over to the optimization stack. Okay, so background for people that aren't familiar, what is image diffusion? How does it work? Image diffusion models, first off, are built on the approach of iteratively denoising some random input until it becomes an image. So for example, if we want to generate an image of a dog, we start with random noise, and we feed it through a model that's trying to take that random noise and given some condition. For example, a text prompt, an image of a golden retriever on a green background. It iteratively denoises that. So you do one step and then you get this intermediate dog, and then you do another step to get the original image. Now behind the scenes, each one of those models, if you're looking at a diffusion transformer, is taking that image, splitting it up into patches. Each one of these patches becomes a token. We do linear projection, then we flatten it all out. And essentially what we're getting is that we're generating this image in token space because each patch is a token, and we're generating everything at the same time. That means that the transformer is getting as input all of the tokens, all the different patches of the image, and it's denoising all at the same time. Now, what if we wanted to extend this to video diffusion? Well, one approach for video models is to say, okay, let's just do the same thing, but concatenate an additional dimension, which is time. Instead of just doing it on width and height, let's also do multiple frames over time. And we're still gonna predict all in the same time, which means we're starting with random noise. This time, not a single image of noise, but multiple images of noise over time. And each step, we're predicting with the model the next diffusion step of all 3 images at the same time. This is called bidirectional attention. Essentially, this means that each frame can see the future frames, it can see the past frames, and you're denoising everything at the same time. Once you finish the denoising process, you get to the point where you have the final video, where you generated all the frames at the same time. Now, one of the downsides of this approach is that it's a batch API. You submit a text prompt, give me a clip of a dog, and you need to wait until you denoise all the frames together until you can finally send the final output of the video. which is why we take the approach of autoregressive video diffusion. Now, the difference here is that instead of predicting all of them at the same time, we're going to predict them one at a time. So for example, you start by predicting just the first frame. Then you need to predict the second frame conditional on both the inputs of the second frame, if it's the text prompts, if it's actions, anything else, and also what we generated in the past. It gets to see the denoised image of the past frames as context in its KV cache. Then we go ahead and iteratively do that one at a time. And essentially, this approach is going to generate one frame at a time. But the main difficulty is that now, instead of the attention seeing all the tokens at once, instead of bidirectional attention where every frame can attend to every other frame, you're doing it one at a time. The first frame needs to generate the entire frame on its own without being able to see what's going to happen in future frames. And then every future frame needs to attend back to that first frame, second frame, etc. Okay, so one more thing that I'll say about this is that there are two challenges in order to get these autoregressive video diffusion models into production. One of them is on the model side, that essentially if you try to train a diffusion model directly to solve this problem of autoregressive video generation, what you're going to find out is that very quickly the model explodes. What does that mean? The first frame you generate is completely fine, but it might have had some very tiny artifact that you can't even see with a human eye. Then the second frame that's getting generated gets in its context the first frame, and it saw that tiny artifact and was out of distribution from training. Because during training, it was used to seeing in its context clean images, which means it'll have a bit more artifacts. And what happens is that with time, the more frames you generate, the more artifacts accumulate until, for example, 10 seconds into the clip, everything turns red. And essentially, that's one of the challenges we have to solve with Decart of how do you do this autoregressive video generation without the model exploding over time? How can you stabilize the models to the point that they can do infinite generation without ever exploding into all red or changing or having bad memory? The second challenge, which is what we're going to talk about now, is the optimization side. Essentially, the difference between a batch API and doing it frame by frame is the same throughput because you're still generating the same number of frames. The main difference is latency. Instead of doing all the frames at once, you're doing them one at a time. Essentially, instead of having a batch size of all the frames together, you're trying to do the same thing, but batch size one, generate one frame at a time. And that means you start to be very latency constrained. And one of the things about GPUs is that GPUs are very much built for throughput. Almost every design decision that went into GPUs over the past 2 decades was oriented mostly towards throughput, trying to optimize on throughput of batch processing, of training, of inference with high batch size. And what happens when you try to take GPUs towards the latency is you start discovering lots of interesting phenomenons, which are opportunities for optimization. So, okay. So essentially, now let's dive into what does it mean to optimize these types of autoregressive video models. Okay, so the first thing is what do we have in that attention? If in the past we said that bidirectional video diffusion has all the tokens attending to all the tokens, here we have something in between, which is that each time you're generating a single frame of video, but your KV cache is all the past frames that you generated. In optimization terms, this is kind of in between prefill and decode from LLMs. Prefill would be the throughput case where you give it all the tokens at once and it just generates all the embeddings at the same time. Decode is where you're generating one token at a time. Here it's somewhere in between because we have a KV cache, which is all the past frames that we generated, but we're generating 1,000 tokens at once instead of doing it one at a time. And this actually creates an optimization problem that's pretty interesting to explore because it gives you lots of different opportunities for optimizations that are much more difficult to do in traditional LLMs. In LLMs, you had either prefill or decode. Here you have something in between, which isn't exactly HBM bound. It's close to being HBM bound, but it isn't. It's doing lots of computation, and then you have different opportunities. So for example, in this case, we're looking at a baseline where you're computing in the attention first QKV. Then if you're doing context parallel, you would do an all gather on K and V, and then you would do attention of Q with the K that you just all gathered, the K from the cache, all the previous tokens that we generated, V that you just all gathered, and V from the cache. Now, this is what you do in a baseline approach. Because what we're doing here has this element of the cache, you can actually split the attention. Split the attention into the attention of Q with the KV cache and the attention of Q with the current KV that would continue the first attention. And then that gives you the opportunity to overlap the all gather. now you can overlap this all gather communication on top of the first attention instead of needing to have it serially. You could even take it further. Attention is normally exponent bound on modern GPUs. So what if you try to overlap on top of the attention from Q, K cache, V cache, not only the all gathers, but also the computation of K and V themselves. Essentially, what you're trying to do, because you're exponent bound, you want to start triggering the exponents as soon as possible. So compute only Q. Once you have Q, start the attention between Q and the KV cache. That starts generating the exponents, and then try to overlap everything else on top of it. So you're overlapping the computation of K, computation of V, and both all gathers on top of that attention, which is exponent bound. Okay, so this was some interesting things on the algorithmic side of optimizations that we can do once you're working with these autoregressive diffusion models. Now we'll dive into what we get to see on the hardware side. One of the main questions that we had, because you're trying to aim for such low latency, you get to the point where your layer time has to be tens of microseconds, 100 microsecond max. When you're at that point of tens of microseconds to 100 microseconds, one of the most critical questions is where do you store the activations? If you follow the normal NVIDIA approach, NVIDIA will tell you have a layer, a transformer layer, it has multiple elements, it has attention, it has gems, it has etc. Between each pair of these operations, store it back and forth to HBM. Now, what we found is that going back and forth to HBM caused too much latency. And we're looking for where else can we store these activations. So the first thing that came to mind is let's look at the L1 cache. Right, we have the L1 cache and shared memory. They're both very fast. They get to roughly 25 cycle access time for the L1 cache, depending on coherency. Shared memory also gets to 55-ish cycles access time. It increases a bit if you try to increase the throughput because of the pipeline. But still, both are very low latency, and they're perfect places to store the activations. The only problem is that they're too tiny. Both of them together are 256 kilobytes per core. You already use almost all of them either to pipeline enough the tensor cores or to pipeline enough the HBM for in-flight bytes from SRAM, which means you basically have no room to store in the L1 or shared memory the activations over time. Okay. After that, we looked at distributed shared memory. For those of you who are familiar, essentially it lets you access the shared memory of other cores directly. The only problem is the exact same shared memory, which means if the shared memory was full, also distributed shared is going to be full because of the same memory that we're accessing. And then we had an idea. What about the L2 cache? What if we tried to use the L2 cache on the GPU to store the activations? So that between different parts of the model, instead of going all the way to HBM, what if we're able to keep it inside the L2 cache? And for that, we did a quick experiment where we're trying to essentially profile what are the different latencies that we'll see when we're going through the L2 cache between different pairs of SMs. The reason you need to do this is because you might have two different operations, one after the other. One that is focused on gems and tiles one way, one that's attention and tiles a different way. And you need to shuffle the data between the cores. So what we see here, this is a benchmark that we ran where a GPU has 148 cores. And for every pair of cores, core A and core B, we're trying to measure the time that it takes to communicate through L2 between A and B. Now, what you see here in this matrix, rows are A, columns are B, and each cell is colored according to the number of cycles that it takes to communicate between those two different cores through the L2 cache. Now, a few funny things that we see here. First, roughly half the figure is yellow and half is blue, right? Which means roughly half the cores are close to each other and half of the cores are further away from each other. Now, there isn't too much documentation on this online. If you look up every documentation on Blackwell, you won't find lots of explanations for this. But if you look at a picture of a Blackwell die, this is a B200 GPU, you'll notice that there are actually two dies inside. The B200 GPU has two different dies. This is the first die. This is the second die. And what we're seeing here is that half of the cores are on die 0, half of the cores are on die 1, which means that we get this asymmetry of it takes 1,200 cycles to communicate between SMs not on the same die and 400 to 600 for SMs on the same die. Okay, that's well and nice. It's also called NUMA, analogous to what happens on CPUs. But what else do we see here? We see these patterns on the diagonal, right? Can you see these 8 patterns on the diagonal? 8 different groups that inside each group it's not only blue, but it's really dark blue. Okay, we go back to this picture of the GPU, and we get to see that the GPU is actually split into 8 regions. This is one of the regions. Each one of these regions, called the GPC, has some of the SMs. And what we're seeing here is the locality of the regions. Now, the best part is that not all the GPCs are the same size. If you look at this picture, this GPC has 16 SMs. These 4 have 18 SMs, and those 3 have 20. Any guesses why not all the GPCs are the same size? Okay. The reason they're not all the same size is at TSMC, they always generate 20 cores for each one of the GPCs. If you look at the picture here of the die and you'd count, you'd see exactly 20 cores inside each one of the 8 regions. But when they generate at TSMC, sometimes they have yield, or they have defects spread randomly across the chip, and that causes some of the cores to be dysfunctional. So what do? They generate 160 SMs, but only 148 SMs pass. And then, according to which SMs pass, essentially they define the GPU. The funny thing here is that this isn't even going to be the same pattern across 2 different GPUs. If you have 2 different B200s, same type of GPU, but different serial number, they're going to get 2 different patterns. And then what we have to do is essentially get to the point where in our API, the first thing we do, turn up on a GPU, run this profile to reverse engineer the exact format of which SMs are in which GPC, and then go from there. Okay, I'll show the last figure, which again is just to give a taste of the type of stuff that you need to push towards in order to do these real-time models at scale in real time. This is HBM. Here, essentially what we're doing is we're sweeping over all HBM addresses. So you're running over lots of different offsets for HBM, and you're measuring the latency that you need to go to HBM. Now, why do we want HBM? Well, if you remember earlier that we said that we want to keep activations in L2, right? We want to keep the activations in L2 as much as possible. What do we have to bring from HBM? The KV cache. The KV cache we have to bring from HBM. It's way too large to store that in L2. So we want to make sure that when we're accessing the HBM for KV cache, we do that as efficiently as possible. The funny thing you see here is that the HBM alternates between 2 different latencies because of, again, the die split. 4 of the HBM stacks are connected to each die, which means they're going to get, according to the address, different patterns for depending on which die you're on, if it's going to be a fast access or a slow access. You also get to see this as a distribution. This is a histogram of the different distributions of latencies, where the last thing you see here is that there's a very long tail. There's 2 very strong peaks, which would be if you're accessing near HBM or for HBM. And there's also a very long tail of, you can go all the way up from 1,200 cycles to, in this case, without load, 1,600 cycles. With load, you can get all the way up to 5,000. That happens because of lots of reasons inside the HBM that we'll skip over today. But essentially, it's another thing you have to be aware of when you're trying to push latency to the limit in order to fit the entire layer of the transformer in tens of microseconds.